before, yeah. Okay, Dustin, go ahead.
Yeah, okay. So we're back to sheaves on locally compact Hausdorff spaces. So we have this pullback and this push forward, and it might seem like the push forward is simpler, but actually the pullback functor is the better one. So, well, pullback functor commutes with colimits, and we prefer colimit preserving functors to limit preserving ones because the colimits are how we build bigger things in general. And also, you know, the pullback of a constant sheaf is constant. This is sort of by definition, but it's that's kind of a fundamental. You want to be able to take your sheaf, and I mean, it generalizes pullback of vector bundles. I mean, it's all kinds of, or not really, but or pullback of local systems or whatever. I mean, it's just kind of the fundamental operation of you take something down here and you move it up there. But the F lower star is a little more subtle, in spite of its simple definition. So the most basic case is when you have X mapping to a point, and then we have the projection P. And then if you take P lower star of the constant sheaf, I'll say work with C vector spaces, then this, well, it's an element in the sheaves on the point with values in the derived category. So it's the derived category. Maybe I should be taking Z. Yeah, there's no reason to take complex numbers yet. And this is a complex computing the cohomology, the sheaf cohomology of X. So in the case where you're mapping to a point, the P lower star is a cohomology. So you might think that, you might expect that in general, this F lower star, so for general F from X to Y, that F lower star is the in families analog of cohomology. But it's not. In fact, there's there's a theorem which tells you when it is. So this is called the proper base change theorem. If F from X to Y is proper, then if you take any pullback, so pullback by a map G, say, then if you take F lower star and then G upper star, that's the same thing as taking G prime upper star, F prime lower star. So cohomology commutes with pullback, and that's the only setting. This is, the lower star commutes with pullback, and in particular, stocks of F lower star are the same thing as cohomology of stocks of the fibers. Sorry. So in this setting, this is kind of what it really means for a lower star to be an in families analog of cohomology, and this just fails when the map is not proper. So let's do a little example. So let's take the punctured plane mapping to the plane. So that's an open immersion. It's basically opposite to a proper map. And then let's take the constant sheaf Z on here. Right. So so we have a missing point here. So we can take F lower star of a constant sheaf, and then we can restrict it to the point. And so we take the stock at the origin. And what is this going to be? I'll illustrate calculating in a purely derived manner, so to speak. So it's the filtered colimit of sections. So I should write constant sheaf Z on U, which by definition of push forward is the same as, so you take the constant sheaf Z on F inverse U, which is the same thing as the colimit of all neighborhoods of, the cohomology of U minus the origin with Z coefficients. And okay, there's a cofinal system of neighborhoods is given just by disks shrinking down to nothing. And when you puncture those, you get something of the homotopy type of a circle. So it has an H1. So this is a Z shifted by 1, minus 1, I guess. Reflecting kind of that the, yeah.
Plus C.
Yeah, reflecting the topology of this space very close to the puncture.
There's also a Z in degree 0.
What's that?
There's also the integers in degree 0.
There's also a Z in degree 0. Thank you. Yes, yes. Yeah, sorry. Yeah, it's the cohomology of a circle. So in particular, it's not the same as the cohomology of nothing, which is the, yeah, what you would see if you took the fiber. So it's more like a cohomology of shrinking neighborhoods of the fiber. Actually, Peter already discussed this more or less, but I wanted to revisit it from different perspective. Okay, so in this sense, F lower star is bad. And the replacement is F lower shriek. It's designed to fix this property of F lower star in a minimalistic way. So F lower shriek is F lower star if F is proper. And F lower shriek always satisfies proper base change and commutes with colimits. So, and you can actually be very explicit about how it's defined, and it's quite simple to motivate as well. So, well, the definition is this. So, well, what is the? It's the derived analog of sections with proper support. So sections supported on a proper subset over the base. So if you have F from X to Y, and you have a sheaf on Y, a sheaf on X, then you want to know what F lower shriek of F is on an open subset V of Y. So you take so you're supposed to take sections supported on a subset mapping properly to Y. So how do you model that? So you take global sections which vanish when you remove the proper subset, and you take the homotopy fiber. So that's like sections here vanishing outside of K. So that's sections supported on K. And then you take the union, turns into a filtered colimit in derived world, overall K subset X, which are proper over Y. So this is a homotopy fiber or a two-term complex, if you like. Oh, where's my V? Where's my V? Yeah. Proper over V, subset Y. Yeah. Okay.
It should be F inverse of B or something like this.
Doesn't matter.
Okay.
Yeah. 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 Okay. So that's the F lower shriek. So it commutes with all colimits and it has a right adjoint. F upper shriek. And it should be no mystery about what this is, right? So F upper shriek of G on a U, basically by adjointness, is supposed to be the Arham from F lower shriek of the sort of constant sheaf on U. Where's my G? Yeah, to G. So if you can calculate, yeah. So you don't have, and in this purely derived story, I mean, it's kind of, you know, I don't know. When I was first learning about the six functor formalism, it was this formalism of derived categories, and it was always, oh, we build this lower shriek, and you know, it's explicit, and then we prove it commutes with all colimits, and therefore it has a right adjoint, which we can't get our hands on. But actually, when you look at it from this perspective, it's quite clear that the right adjoint is something you just know what it is. It's described by this formula. So you can calculate the compactly supported cohomology of this basic so-called extension by zero sheaf, and you take its dual, and that's the sections of the F upper shriek, and there's nothing particularly mysterious about it. And you definitely don't need the adjoint functor theorem to prove it exists. Okay, right. So this is the six functor formalism, and I said the kind of thing it's good for is proving duality statements. So, so for example, so it's good for duality. So e.g., there's a theorem, I guess, of Verdier. Okay, but it's Poincare duality, basically. So if, say, M is a topological manifold, then for the projection to the point, we have, well, F upper shriek of an arbitrary thing is the same thing. Well, this is quite formal, I guess. F upper star tensored, and that's always implicitly derived tensored with F upper shriek of the constant sheaf. So then you really want to know what this is. And this is the same thing as the orientation sheaf sitting in degree D, where D is the dimension of the manifold. So yeah, so if it's an oriented manifold, it's just this would just be Z, constant sheaf Z. And this you can prove this locally. So the proof is basically for an open subset, you can kind of just look at the definitions. And for the inclusion of an open subset, you can kind of just look at the definitions and see that these things are the same. So that means that this this construction of p upper shriek of Z localizes on M. So in principle, if you're trying to look, if you have an object and you're trying to understand it locally, but it's only an object in the derived category, then you're kind of in trouble. It's not enough to identify it locally. You also have to know how it glues together, and this can be quite complicated. But if you do prove that locally it sits in a single degree, then that means that globally it also sits in a single degree, and the gluing problem is just it's only a one categorical problem, and so it's actually quite easy to understand. You just have to see how homeomorphisms act on your thing. So in fact, this localization, since it lives in a then you check on RD basically that P upper shriek Z is orientation sheaf sitting in degree D, and then you're done. And this is just I gave you the formula for P upper shriek, and this just follows from the fact that compactly supported cohomology of RD is just Z, Z shifted by minus D, which you can prove by compactifying to a circle, for example. Okay. So that is a kind of a Verdier kind of formulation of Poincare duality, but how does it imply the classical Poincare duality? Well, we take a special case of a corollary. So if we take the P lower shriek of the constant sheaf, well, this is a complex computing the compactly supported cohomology of M. If you look at the definition, you'll see that this is a complex computing the compactly supported cohomology of M with Z coefficients. But then by adjunction, this is the same thing as R-hom from Z to P upper shriek of Z, but R-hom from the constant sheaf is the same thing as derived global sections. sorry, I should put the orientation sheaf here, right? And that's the cohomology of the orientation sheaf with a degree shift. And now you're seeing that the dual of compactly supported cohomology is the same thing as cohomology with the orientation sheaf. And if M is compact, this is cohomology, and this is derived dual of cohomology, and it'll turn into homology, and you get the familiar statement of Poincare duality. Yeah, so anyway, that's the kind of thing we're going to essentially be mimicking in the complex analytics setting by inputting this this notion of liquid theory applied to the holomorphic functions. So okay. Well, are there any questions about that? It's kind of brief and sketchy introduction to 6 functor formalisms. All right. So now let's take I'll just work with Riemann surfaces again for simplicity. So now X will be a Riemann surface. So now for an open sub, oh no, sorry, I forgot, I'm sorry. There's one more thing I want to mention about the purely topological context. Well, recall that a locally compact space is locally compact. So it makes sense that the sheaves should also be determined by their values on compact subsets. And indeed, this is the case. And actually, I saw the first place I've seen this explained, or exactly how that works is Lurie. And I don't know it in any classical sources. And but anyway, Lurie did it in the derived setting, which is what we want anyway. But so I'll put his name here. So we'll go back to our, sorry, X is still a locally compact. I mean, it doesn't really have to be finite dimensional for this Hausdorff space. This embeds fully faithfully inside sheaves on the site of compact subsets. Values in the derived category. And here it's just a topology of finitary unions. Which is essentially, we're essentially imposing Maya via torus for covers. Yeah, if you have, for closed, for compact covers. So it's a finitary topology in contrast to the infinitary topology here you see in locally compact Hausdorff spaces. And the functor, and the essential image is those sheaves on compact subsets G, such that if you take the value on a compact K, it's the filtered colimit over all compacts, and this double inclusion notation means K contains an open neighborhood of, K prime contains an open neighborhood of K. All right, G of K prime. So you have this extra sort of continuity condition on the values on your compact subsets, and that singled out this full subcategory here. And the functor in one direction.
I think we should call this condition over convergence.
Yeah, that's what it is in the, for the p-adic people, they call this over convergence. Yeah. I guess there's some analog of that of this in relating sheaves on the Berkovich space to sheaves on the adic space, right?
That's right, yeah.
So this is kind of like sheaves on the Berkovich space, sheaves on the adic space, and this is analogous to Huber's, Anyway, let me go back to being a blissfully simplistic topologist for a second. Right. And so what are the functors going back and forth? So if you have a sheaf on X, then you get a sheaf, well, I'll call it F again, but F on a compact is the colimit are all shrinking open supersets of K. It's also the same thing as global sections of the pullback along the inclusion from K to X of F. So it's also just the same thing as pulling back to K and then taking global sections. It's not entirely obvious that those are the same, but it's also not difficult to see. And on the other hand, if you have a F in, maybe I was calling it G, in sheaves on compacts, then you get F on an arbitrary open by taking an inverse limit overall, growing compacts inside you. What's that?
G of K. G of K.
G of K, thank you, yes, yeah. Okay, so this is going to be, it's going to be more convenient for us to, in the holomorphic context, to work with values on closed disks than open disks, because those are going to give dual nuclear Fauché spaces instead of Fauché spaces. So that's why I wanted to mention this second point of view on sheaves on a locally compact Hausdorff space. Okay, so now let X be a Riemann surface. So we're gonna, so then for an open subset of X, we can associate the ring of holomorphic functions. Viewed as a condensed ring, or in fact, liquid. C module. And well, that's one way of describing. Actually, you can directly describe what it is as a condensed real vector space. So if you have a compact Hausdorff space, for example, then maps from this to O of U, these are the same thing as continuous maps, S cross U to complex numbers, such that if you restrict to U along the inclusion of any singleton in S, such that this is holomorphic. So it's, in other words, it's just continuous families of holomorphic functions, just like you would intuitively expect. And again, yeah, things like Cauchy integral formula and so on will prove that this is the same as, for example, considering holomorphic functions as a closed subset of C infinity functions with its usual Fauché topology, defined by the kernel of the Delbar operator. You can see there are that all sorts of possibilities for the topology or condensed structure on holomorphic functions are the same. Okay. And note so that so then if we take sections on a closed disk contained in X, this recovers what we had before. Over-convergent holomorphic functions on D bar. So I mean, in the sense of this, we're asking now the value of our sheaf on a compact subset, and the definition was there's the limit over the values on the open subsets containing it, and so it's consistent. Okay. Right. So now this is so we have a and it sort of clearly satisfies the sheaf property because well, yeah. Yeah, I don't know, it does satisfy the sheaf property. So anyway, so now let's consider the derived category of all right, sorry, consider sheaves of derived liquid C modules on X with an action of this structure sheaf of holomorphic functions. So sheaves of O modules on this topological space, but where the sections are condensed vectors or liquid vector spaces instead of being ordinary vector spaces. We'll define a quasi-coherence condition on these. So here's the definition. So such an M, such a sheaf, an O module sheaf, is quasi-coherent if for all inclusions of closed disks, again, it's always going to be derived liquid tensor product. So just because of the module structure on here, we're going to have a natural map like this, and we demand that this be an equivalence. So it's if you're familiar with the classical theory of quasi-coherent sheaves in algebraic geometry, it's exactly the same. Treating closed disks as kind of analogs of affines. And okay, to be more honest, we should of course allow things slightly more general than closed disks, some kind of compact Stein manifold of some sort, because the intersection of two closed disks isn't exactly a closed disk, and we'd like to have things closed under intersection, but that actually doesn't really make much of a difference.
I think as a definition, that's good, right?
Yeah, as a definition, it's still correct, yeah. But in practice, we would want a little more flexibility with the basic affines. Yeah. Right. So that's a natural thing. You might wonder, why are we using the closed disks instead of open disks? You might think, yeah, why not the analogous definition with open disks? Well, yeah, it turns out you can make a definition with open disks. It's just a little more complicated. It wouldn't be just a standard algebraic base change in the liquid world. You'd have to do some further localization of some sort, which I'll be hinting at it a bit later. But and essentially the reason is that these overconvergent functions, being a sequential colimit of compact projectives, are just much more convenient to work with algebraically than the ones which are inverse limits of compact projectives, the nuclear Frechet things themselves. Okay. So then now we can define functors. So, well, for a map from f from x to y, actually we'll only be interested in two cases. Well, one is an inclusion of an open subset of x, and the other is projection from x to a point. Those are the only things that are going to be relevant for our argument. So you can keep those two cases in mind. Functors, the lower star and lower shriek versions, exactly as in the topological case. And then the claim is they preserve quasi-coherence. They send O modules to O modules. So this, it might be a little bit surprising that the lower shriek preserves quasi-coherence. And I was planning to say a couple of words about it, but I think I might not have time if I do. Oh, wait, no. Oh, wait, I have a half hour left, right?
Yes.
Yeah, okay. So maybe I'll say a word about the lower shriek preserving quasi-coherence. Of course, in the second case, it doesn't, oops. In the second case, there's nothing.
About the F-lower star commutings reserving quasi-coherence? Is there some claim that something commutes infinite products in tensor product?
No, no.
Is there some assumption about F then for the F lower star preserving quasi-coherence?
No, so the lower shriek is always going to be described in terms of colimits of sections on compacts.
Lower star.
Oh, the lower star. Yes. No, I'm sorry. Yes. Yeah. Wait. Yeah. That's bad. Yeah. That should. Yeah, that's not true. My mistake. Yeah, I actually didn't even want to claim that. Sorry. Yeah. The lower shriek. Yeah.
No, I mean, maybe this is true though. I'm confused about something.
I don't think so. I mean, it's conceivable, but I don't know, maybe. Okay, we won't need that. In fact, we're going to focus on.
I think it is true actually.
Oh yeah.
I think it's true. Yeah.
So you think you can take it? What you're saying, like if you take a dual nuclear Fauché space, tensoring will.
No, I'm not claiming anything. The statement you've written is, I think, correct, and not claiming anything general.
Yeah. Okay. Well, that's good to know.
I mean, basically because there is some kind of steady localization, and steady localization somehow commutes space change.
But these aren't nuclear, right? I'm not restricting to a nuclear full subcategory.
Yeah, don't have to. Because you can write this localization also as an R-home from something else, and the R-home, of course, commutes this product.
Yes. In fact, yeah.
Right.
I was gonna write this. Okay, let me get to So I agree that that's the main point. So why don't I get to that, and then we can decide at that point whether it proves the claim or not. So sorry, sorry about. So I was exactly intending to explain that. Right. Yeah, I want to remark actually. So there's this kind of curious. If you want to take a F lower shriek of a sheaf. So it's supposed to be a sheaf of condensed things. So it's supposed to have a value on an extremely disconnected set, which is just a sheaf of ordinary things. And this is going to just be the F lower shriek of, the F lower shriek of the sheaf you get by evaluating F on S. So these extremely disconnecteds commute with everything, like I said. So in fact, for a lot of properties of F lower shriek, like if you want to know the F lower shriek commutes with colimits, you can immediately reduce to the classical case, or you could just run through the arguments in the classical case as well. It doesn't matter. But yeah, with this kind of remark, you can just reduce to the classical case. So right. So the point is, so F lower shriek will by this argument will commute with colimits, and therefore has a left adjoint or right adjoint. Sorry. F upper shriek, and the key will be to prove that so the duality theorem is essentially going to be that again F lower shriek of a arbitrary V is the same thing as F upper star of the tensor F upper shriek of complex numbers, and the complex F upper shriek of the complex numbers is this bundle of one forms sitting in degree 1. Right. Yes. I also want to say that in this case, J upper star preserves quasi-coherence. So the J upper star, if you're thinking in terms of sheaves defined on compact subsets, then this just restricts to only looking at complex subsets inside ZU, but then everything else is the same. So it's just forgetting some of the data, and then that preserves quasi-coherence. Right. So what is going to be the key to this? Well, we're going to work locally again, and so we have to understand what's going on. But now we can't work locally a priori. We can't work locally on a closed disk because for a closed subset, the F upper shriek and the F upper star are not the same. So we're only allowed to localize for open subsets. So the key is to understand what this quasi-coherent sheaves looks like on an open disk D. And the claim is, well, but I still want to phrase it in terms of a closed disk. So I'll put D inside a closed disk. Oh, well, I guess there's an easy way to do that, isn't there? So I'll put D inside a closed disk, D hat. So then there's so I claim there's equivalence between quasi-coherent sheaves on D and a full subcategory of O of D hat modules in liquid vector spaces. And which full subcategory is it? So it's those modules M such that if you take M tensor O of D hat with O of D hat minus D, so the boundary, then you get 0. So let me explain what the functors are in both directions. So the functor, well, there's an obvious functor in this direction. So this sends a module M. It doesn't have to satisfy this condition, in fact. You just send it to the sheaf, which is described by, on any closed disk E subset D, you take the sheaf M O of D hat, O of E hat. So you just take the algebraic base change from this functions on this closed disk here. And then that will automatically be a sheaf and satisfy the quasi-coherence condition. Right. And the functor in the other direction is given by taking so if you take your sheaf F, you send it to right. Right, but let me write this in more familiar terms. So you can take, so well, one way of describing it is, I guess, I don't want to describe it like that.
Can you not consider F just as an O of D bar module and then take the cone of the map?
Yeah, but yeah, I don't. Yeah, but I don't think I'm just allowed to consider a sheaf as an O of D bar module. Oh, I guess. No, I guess I am. That's right. Yeah,
the global
it's an
sections.
Yeah. Yeah. Okay, that's good. Okay, I like that. Yeah, the global sections of. Yeah, that's right. Yeah. Right. Yes. Oh no, fiber. Sorry. Yeah. So all you need to check that these are inverses is these tensor product rules for disks. The fact that tensor products of disks turns into intersections. So it's there's nothing special going on here. It's just a matter of we know how to calculate everything, and so it's not difficult to prove any of these things. I guess a priori here, I was going to write it a different way. A priori here, we have to control a tensor product with a nuclear Fauché space. There's another way of writing it where you don't have to do this. My pen couldn't figure it out in the moment. So I was going to try to write something different, but yeah, my pen couldn't quite figure it out in the moment, and I apologize for that. But anyway, so the point is, the remark you want to make is that this functions on d bar minus d is an idempotent functions on d bar algebra. So quasi-coherent sheaves on D is gotten by killing from O of D bar modules by killing an idempotent algebra. And this gives descriptions of all the functors. Yeah, P upper star, for example, of a vector space V is going to be gotten by, so you take R HOMs in O of D hat modules from the fiber of O of D hat, mapping to O of the boundary of D hat, to V tensor O of D hat. So you take what would be the upper star if the category of modules were just O of D algebras, and then you have to localize that. And the way you localize in the setting of killing an idempotent algebra is by R homing from the fiber term.
Is it P upper star or P upper shriek?
That should be P upper star, yeah.
Wait, but this fiber says it shouldn't, you're homing from some fiber, and shouldn't the fiber be the P lower shriek?
Oh, sorry, was this, I may have gotten things mixed up here, I apologize.
I mean, P upper star of V should just be V tensor O of D bar, right? Or?
No, because that's not actually,
Well, okay,
that's not actually in this category, so I have to put
just
it.
V tensor O, so P upper star of V is just V tensor. It's just V tensor structure.
Oh, yeah, but the question was how you write that down. So that, yeah, so you want it to just be this, but that doesn't actually live in this full subcategory. So you have, the way I described it. So then you have to put it there.
But then it just takes this cone again, this fiber again.
Okay, so I wasn't supposed to do the R-hom there. Okay, I'm sorry, guys. This was, I guess it's been a long week.
This was P up. I mean, it's okay. It's a formula for P upper shriek. It's anyway what we're interested in. So.
Okay. Yeah. So that, yeah. I mean, it is just straightforward to work it out. I just wrote down the wrong thing, and I apologize for that. Thanks for catching all my mistakes, Peter. I'm very happy you're here. Right. Yeah. So the point is, you're essentially just reduced to calculating what this fiber of O of D hat mapping to O of boundary of D hat. Yeah, and this is actually just a calculation you can do on the level of rings of convergent power series and so on. And you can see that, well, I said fiber, it's a homotopy fiber. It turns out this map is injective, and the co-kernel identifies with, well, one forms on the, I guess what's the nice way to say it? So you take one forms on the complementary disk in P1, say. It's going to look like another ring of overconvergent power series. So yeah, so if you take your D, if this is your D bar then you can look at, you can add a point at infinity to your affine space, and then this is then the complement of the interior of D bar is just another closed disk. And what this is canonically, if I wanted to say things independently of coordinates, it would be one forms on the complementary closed disk. But if you just calculate things, you'll see that it is just another, just another version of functions on the closed disk. And this is what turns into the Serre duality claim. So when you look locally, okay. I've gone over to, oh no, I have 15 minutes. I keep on thinking, okay. So let me extricate myself from these computations here. So what do we have as a conclusion? So we have that P upper shriek is the same thing as P upper star tensor with this dualizable, this vector bundle here. So now we get a corollary from this, which is that, so note that this commutes with all colimits. So, i.e., the right adjoint of P lower shriek commutes with all colimits. It follows that it sends follows that P lower shriek sends compact objects to compact objects. Now, a vector bundle is dualizable. Hence, it will be compact if and only if the unit, just the constant sheaf, or the structure sheaf, sorry, is compact, which is the same thing as asking that P lower star commutes with all colimits. So the conclusion is, if P is proper, so if X is compact, well, we get that the lower shriek of any vector bundle, but lower shriek is the same as lower star in the compact case. So the lower star of any vector bundle is a compact object in liquid P. Okay. On the other hand, well, for any X, oh no, let's just work with compact X. It is by definition, a limit, a finite limit of these, of D bars. So if you just cover your compact Riemann surface by disks, by finitely many disks, then you'll see that your global section functor is always determined, always determined, glued from its values on the disks there. That implies that it's nuclear in the sense that I'm about to just remind you of. So then we use the nuclear. I'm going to remind you about this plus compact equals perfect, and we conclude finiteness. Finiteness of cohomology, R gamma X V. Okay. Right. And then to finish and get, then you can finish and get Serre duality in exactly the same way as how I explained that you get Poincare duality from the Verdier kind of formalism in the topological case. So once you know this is a finite dimensional vector space, then you can take Hams out of it and you can just calculate away using the adjunction between lower shriek and upper shriek, and you get Serre duality. Just as in Verdier setting. Right. So let me recap here. So there's a bunch of fluffing around with calculations and everything, but the key was we had these relative tensor product calculations of closed disks, which meant that the algebra reflects the topology. And that gives us a good category of quasi-coherent sheaves. And then to prove these fundamental facts about Riemann surfaces, which are the basis for everything, for example, the fact that compact Riemann surfaces are algebraic curves and all sorts of stuff, the whole formalism of liquid modules, if you take it all for granted, it just reduces you to one calculation of what the co-kernel of this map is. And that's just some explicit thing you can see with power series, if you like. That gives some local information, and then the whole liquid machinery in this quasi-coherent formalism, you just turn the crank and you automatically get these two major theorems in Riemann surface theory, which are kind of the basis for a lot of things. But there's one big thing I didn't explain, which is what I didn't, well, I talked about nuclearity in the p-adic context, but maybe I should remind you in this context. So recall, well, in the p-adic setting, we defined that M to be nuclear if for all extremely disconnected S, continuous functions on S with values in the ground ring, in this case it'll be C, tensor M on a point mapping to M of S was an isomorphism. Now, there are two major differences in the liquid setting. So first of all, this is not, as far as we know, this is not a good definition. So Banach spaces are probably almost certainly not flat with respect to the liquid tensor product.
Why do you say it's not a good definition?
Because I didn't put derived anywhere.
Ah, okay.
Yeah.
Okay.
So in the when I was discussing this in the p-adic setting, I had a nice underived definition, and it worked well because this guy was flat. But in the nuclear setting, in the liquid setting, sorry, this is a Banach space, and Banach spaces do not behave so nicely in general with respect to the tensor product. So we better derive this tensor product, and we better make this a definition for an element in the derived category of liquid vector spaces. And so we don't know whether there's a T structure or whether this is closed under T truncation. Under passing to homotopy groups, for example.
Wait,
so
I thought you had an argument for this once?
What's that?
I thought you had an argument for this once?
I did have an argument for it once. And then I discovered my argument was incorrect. So, yeah.
I'm not up to date, okay.
Yeah, no, I told you for sure, but
yeah, okay.
Right. So we have to just work with derived things everywhere because of this reason, but in the practice, it doesn't mess anything up. So for the kinds of things that show up in complex analysis, or whenever you're in nuclear Fichet or dual nuclear Fichet, your derived tensor products are going to be concentrated in degree 0 anyway. So it's just for foundational reasons we have to do the theory derived, but it doesn't actually introduce any real complication. And this is going to be the same thing as it's generated under colimits. In fact, freely generated under sufficiently filtered colimits by the basic nuclear. So these are trace class maps in the inherent P liquid setting, and these are compact projectives. A special case is where all the maps are inclusions. And then you get exactly these dual nuclear Fichet spaces, the classical dual nuclear Fichet spaces, by kind of similar arguments to what I explained in the first half. So all dual nuclear Fichet spaces are basic nuclear, in particular they're nuclear. But then the nuclear is closed under all colimits, under all finite limits. So this will help justify, this claim that your R gamma is going to be a nuclear thing. Right. So then, and recall also, this was a general thing, that dualizable, this is a general fact about some certain kinds of tensor categories, is the same thing as nuclear plus compact. So then to justify that nuclear plus compact is dualizable, you only have to, is the same thing as a perfect complex, then you just have to check that dualizable is the same thing as perfect. And there's another fact which is nice, is that this is generated by cones of 1 minus f's, where this is a compact projective, and f is a trace class map. So you have to, you have to prove the liquid analog of a very basic fact in functional analysis, that if you take a trace class operator, in fact, a compact operator on a Banach space, say, then 1 minus that will have finite dimensional kernel and closed image and finite dimensional co-kernel. So in the p-adic case, there was a nice algebraic argument for, neither of these are discrete, yeah. Discrete relative to the condensed structure that already exists on the complex numbers. Yeah, in the p-adic case, there's a nice algebraic argument for this, but in this case, I don't think you can do anything other than sort of mimic more or less classical proofs. In fact, you can deduce this from the classical one, because you know a priori that such a thing is going to be dualizable. So it's enough to analyze its dual. And the dual of a compact projective is a Banach space of continuous functions. And you can check that the dual of a trace class thing is going to be a compact operator between these Banach spaces. And so actually you can deduce that the dual then is going to be a perfect complex, and therefore by dualizing back again. So actually this exotic variant follows from the standard variant, but you could also prove it in similar ways to the standard variant. Right. So I think that finishes what I was intending to talk about. Again, I apologize for all the gaffes, and thank you all for listening in.